Our topic today is Navy's 50-year safety record of nuclear power generation. With me today, Ronald Stein, Senior Policy Advisor on Energy Literacy for the Heartland Institute, and CFACT is an engineer and co-author of Pulitzer Prize-nominated book Clean Energy Exploitations, and a new friend, Dr. Oliver Hammers, doctorate in physics from the Institute of Radiation and Nuclear Physics at the Technical University of Berlin, Germany, researcher in physics, executive director of UNLV's Harry Hyde Center. Welcome, Ronald and Oliver.
Armando, glad to be aboard.
Thank you for having us.
Excellent. Let me start with a point that's very curious for me. The U.S. Navy is a monster of big quantity of Navy ships and so submarines. This systems works with several decades. I don't know, 4, 5, 6 decades. It started
five decades since 1975. Yeah.
Why nuclear? What was the option for nuclear? Because the energy density, security, safety. What's the reason they choose nuclear for this situation?
Well, I'll go and then I'll let
Go ahead,
Oliver come. You talk about the aircraft carriers. I mean, these are huge. They're like the 3 football fields long, and you're traveling all over the world, and they basically need fuel, and to depend on it when you're going around the world. And the same thing with submarines. And so they did it for, I think, national security reasons and for reliability reasons. And, because they have continuous dispatchable electricity that's available. And in those 50 years, there's now 6 aircraft carriers out there. There's more than 40 submarines out there from the Navy, all being run by nuclear power. They've had a great safety track record. And, like I say, they've got reliable dispatchable electricity to run these monsters. And we're investing in wind turbines and solar panels. I'll let Oliver elaborate.
Well, I think that, for the Navy, the demand for power started on the submarines, which was more like 75 years ago. So way before the 50-year deadline or the number that we used in that article. But
75.
The submarines, you cannot have open fires really in a submarine, and there are no windows to let some fresh air in, and so
no fresh air.
You're effectively you're struggling to get the electricity to, and when you see these watch these old movies with these old submarines, they have battery banks, and those battery banks got recharged, and they're mostly run on electricity, right? So they already come from the idea of using electricity for a lot of their functions in their submarines. And of course, the submarines' mission was to stay underwater as long as possible. So that means refueling is not really an easy option, right? So you want to stay underwater for months and months and months. And I think that's where the idea came from, to have electric power generated by nuclear, where you don't need to burn diesel fuel or whatever, in the more modern world. Not just coal. In the past, the coal, the Titanic had these huge boilers for coal power, but
wow.
Then diesel fuel came, and then the whole shipping got revolutionized. But even for the submarines at that point, it was not really feasible, because you needed to refuel, right? You need to refuel for the producing the electricity. And so nuclear was the only option that really allowed it to stay underwater for months at a time, right? Like stay underwater for 6 months and operate. and that's where it came from originally. So you could expand the 50 year back to 75 years or 80 years, right? When the first, I think it was in the 1950s, where the first submarines kind of came up with nuclear power, and then that's kind of where it then evolved into other applications, other ships and everything, right? So it's yeah.
And what other countries use the same solution? I know that Russia is one of
Yeah,
them.
Russia uses, of course, the same ideas, right? I think these days, nuclear, the submarines, they're all nuclear powered, right? You don't, because they all need to stay underwater for many months, and
Many
so
months.
there's no other option
No,
than
no other
use
option.
nuclear. Yeah,
Yeah,
exactly.
yeah. But going to the military systems, to the civil systems, I mean, the US has 20%, I suppose, of the country's electricity coming from nuclear before California start closing.
That's right. Yeah.
Yeah. But what's happening now? So the idea is to grow this participation of nuclear or not grow? What's the logic behind this?
You mean on land for the civil use?
Exactly.
Yeah, exactly. Yeah. Well, the nuclear power has an extreme high energy density, right? The uranium that is used to create energy is so dense and so powerful. Is about 50 million times more powerful than burning a carbon atom to CO2, right? So you have get 50 million times that. So effectively, when you have a coal power station, and in the coal is uranium traces just naturally occurring. That uranium has more energy than the entire coal. So that gives you an idea how much density of energy is in the uranium um, compared to the classic burning process of energy generation, right? And so that's why it is a very clean, a very reliable background, always on kind of solution for electricity, and has a lot of benefits, especially over the classical systems or the renewable energy systems and stuff, right?
But
Well, the thing
Ronald,
that's really
the,
neat is that over in France, they have 50 nuclear power reactors producing about 70% of the electricity of France.
France
And as
exporting to Germany.
That's right.
I don't know, and as Oliver mentioned, the amount of energy in that product is amazing. Well, they're able to, they got a lot of waste, but they're able to recycle like up to 96% of it. It's almost like perpetual energy that can
Yeah.
recycle.
Well, I give you an example of maybe how you can look at the classical power systems, the classical nuclear power systems. If you would have a car and you would fill it up with gasoline, and you drive that car now for 12 miles, and then you take the rest of the gasoline out and put it in a barrel and then want to kind of put it in a waste dump, and you refill the car with new fresh gasoline and drive another 12 miles. This is kind of how the current nuclear power generation works. So what we kind of looking at is to propose a different type of nuclear power generating system that would take the remaining fuel and drive another 388 miles with it, right? So that even though there's this immense density, it's not even utilized in the current light water reactor power systems because they're all based on the idea that was developed in the Navy, right? The Navy wanted, Richthofen said, I'm swimming in water with my boats, so I use reactors based on water. And that's where these reactors came from. When they would have said, I swim in molten salt, and that's why I use molten salt reactors, then we would have complete different type of nuclear power systems. right?
Uh-huh.
And so that's where effectively the history comes from, that we have this type of nuclear power plants as we experience. Yeah.
And Ronald, why? What's the reason that's so high rejection to use nuclear? It's only
In the
safety.
United States,
United States, everywhere in the world, including Germany.
politics.
Well, yeah,
So
you
simple. One word.
And the discussion.
you can say it's effectively communist propaganda that emerged from Russia to effectively make the power as expensive and less accessible for the Western world. So the Soviet Union at the time would have an advantage. In addition, they would sell their natural gas, right? So by kind of getting rid of nuclear as a base power in the Western world, especially Europe, they effectively developed the market for the gas, right? And that natural gas, and that's kind of, there's a decades long scheme behind it. It's not something that happened overnight, but the Western societies fell for the trick by the Russians and the communists, believing that nuclear is bad, and started to shut down their nuclear power stations. Right, the only ones holding on are the French, and maybe they're smarter than the rest of Europe, but they like the cheap power from those power plants.
Well, when you take a look at Asia, there's 60 reactors that are currently under construction. There's another 110 planned.
Wow.
Most of those are in Asia.
Yeah.
And we're building wind turbines.
Yeah, exactly. Yeah,
Wow. Impressive number, huh? Impressive.
yeah,
But in the article you both wrote this week, you mentioned two important points: small modular reactor (SMR) and
yeah,
fast breeder reactor (FBR).
yeah.
What are they like? What the size? What the capacity? Please tell us a little bit about these details.
All right. The fast breeder reactors are the ones that using fast neutrons to create more fuel than they burn in the fission process during energy production. And so they could use what's called the spent fuel, which effectively is a fuel for breeder reactors, right? It's not that the fuel is not spent. It's just not usable in the light water reactors that are out there, but breeder reactors run on it, right? So it's effective for one, it's a waste product for one side, but the other side said, hey, I'll take that to run and make a lot of power out of it. They can make 30 times more power out of it than what the light water reactors created in the first place. So, and these are the fast breeder reactors are effectively similar in size as the light water reactors and the gigawatt range, per reactor. So they would, in the long run, replace the light water reactors and produce electricity in a large scale. Now, small modular reactors they're kind of the tool chest, to say. They are not breeders. They kind of still use the light water technologies and other kind of, there's a whole slew of different types of processes, but they effectively can produce a lot less power. And so the advantage is when you have a system that produces a lot less power, they can be built much safer. You don't need a lot of the redundancy and overhead from these big light water reactors that you have. You can make them in a small scale. There are some that go down to the megawatt level, so they could power like, a couple of hotels or, some small industrial applications that produce heat, that produce power for systems that can be even off the grid. So they built their own little microgrid and have their own reactors running, and they're not tied into the main power grid from the power companies that are out there. And so it gives so much versatility to different types of industries, to different types of applications. You can deploy those things into disaster areas. I'd say there's small town hit by a hurricane, you can deploy those reactors and effectively produce a couple of megawatts. They go up to like 300 megawatts. Eventually they kind of become more like the classical reactors, but a couple of 100 megawatts is still a good size. And then you can provide power in disaster areas, or the military wants it when they set up a base, right? They have a small reactor that is just in their own grid environment, in their own kind of base, and just provides power for them. And that's
Actually, I've got a question for Oliver. We're basically the wealthy countries are focusing on building wind and solar. The problem is of the 8 billion people on this earth, more than 80% are making less than $10 a day. So we got 6+ billion people that can't afford to build wind and solar because they can't subsidize themselves out of a paper bag. So isn't the SMR basically the potential lifeblood to bring electricity to the 6 billion people that basically have nothing? They've got no sanitation, no clean water. I mean, it'd be just like a military opens an operation in La La Land. Yeah, you can basically get an SMR and provide electricity for them. Isn't this the light at the end of the tunnel for these 6 billion people, for them to get electricity?
Yeah, it's a lot easier to set up those systems on small, even on concise size grids, subgrids. They don't need a big super grid that powers the whole whatever regions or countries, right? You can really deploy them in critical areas. These things can make clean water. They can provide clean and cheap, electricity. And effectively, you could turn any region in the world into an economic powerhouse by providing cheap electricity that is also kind of can be used to make clean water. And so you cover the basic needs for the population, right? And so you get away from all the expensive solutions. Africa cannot be helped with solar panels and windmills, right? I mean, it's way too expensive. So you need to have solutions that are way more affordable, more adaptable to the size of what they need in a certain region. If they only need a megawatt, you just provide a megawatt, right? You don't build a power plant as a gigawatt, right? So you can really tailor those systems for applications of whatever situation you encounter and where you need electric power, right?
I guess the point I was trying to make is instead of subsidizing wind and solar that generates unreliable, non-dispatchable electricity, instead of subsidizing wind and solar, we could subsidize SMRs and improve humanity around the world. I think there'd be a lot more people benefiting from that than
solar and wind.
That's right.
Wind and solar.
Effectively, you help the people to help themselves and build their own world on that.
But let me ask you both: is just commercial, both SMR and FIBR, or is still in research phase? And which size is a big one? 1 meter, 10 centimeters. What's the size of this equipment?
Well, the smaller systems. I give you an idea of the new type of power systems. Okay, you can maybe compare to cooling. Let's say you want to cool a house, you build a new house and you want it cool in there, and you build an air conditioning system. So the contractors come to the house and put down all the pipes and all the whatever they need to kind of make the air moving through cooling systems, and so you have a cool house when you want it cool. Now the new reactors are more like refrigerators. The refrigerators are not built in your house. They're built in factories and then shipped to your house.
Yeah.
And that's kind of the idea for the new type of reactors. You build the reactor or part of it, or some components, and effectively you have like a refrigerator, a factory setup that can make this a lot cheaper. So therefore, the cost for those reactors, this type of power systems, especially when it goes into mass production, when thousands of those things get built and deployed, the costs are coming down tremendously, right? It will by far be the cheapest form of electricity that you can imagine, right? The other thing is you can ship them on a flatbed truck to either the whole unit, or when it's too big, of course, you need to assemble it, have a couple of trucks and then put the pieces together. But the point is, you have easier to deployable systems that you do not need to have like a construction site and build like for years a system, right?
So Oliver, what you're saying, when I go on Amazon to order my power drill, I can also order an SMR.
You wish. The only entity that can actually order SMRs is the military, right?
Okay.
Where in the United States?
There are several companies in the U.S. that work on this. A small one in Texas, X Energy, that build pebble bed reactors, which go down to really to the megawatt level. And then there's NuScale. There are other kind of systems that are in a range and that go up to hundreds of megawatts, right? But the Regulatory Commission for the commercial side is putting up a lot of barriers for the sale and deployment of those systems.
Why?
Well, it's an agency where people get paid very well to do not much, right?
Motion is progress.
Well, you have to look at maybe from their perspective. They don't get a benefit when they approve a system. They don't really get a benefit when it works, right? But when they screw up, let's say something goes wrong, then suddenly they're on the line, right? So you have to be, I was a little facetious here, but they kind of don't really have a good incentive to move these things along, because the losses are big and the gains are nothing, right? So
you mean that's comfortable to do nothing?
Well, they're working toward retirement.
Well, I don't know. Government employees always work a little different than the free market enterprise employees, right?
Let we go to a controversy point.
Yeah.
Safety is something that pay attention.
Yes.
I saw this yesterday. September 17th. Nuclear plant radioactive leak slowing down.
Yes.
So this kind of material is so complicated to understand. Could you please explain to us?
Well, this is most likely that because there's only light water reactors out there, right? The way they operate with water cooling and so on, they are not built to the same safety standards than the current reactors. So you can say this might be a generation 2 reactor, and we are now at the generation 4. That means those reactors are built with redundancy and where you have effectively safety procedures in place from the cores. Let's say the core is liquid, for example, right? So you cannot have a meltdown because the core is already melted, right? So you run the process through a molten substance, and that is much easier to control than when it just rods and pellets and so on that could melt potentially, and then of course you have no control, right? So the systems are built now that you can put them underground, and almost depending on what type of system is, you could effectively lock the door and walk away, and it keeps running just for decades, right? So there is a different type of built-in safety systems in these new designs that go way beyond these old designs where you can have water leaking out and there might be some radioactive contamination in there, or you have tritium buildup from when something goes wrong, like what we saw in Fukushima, right? And so you have systems that if you have problems like in Fukushima where the power goes out and you don't have power to run because the diesel engines don't operate when they're underwater. And so all these kind of problems you don't have with these new reactors, right? They're kind of self-cooling. They designed to keep things. They shut things down automatically when it goes out of whack, right? So there are different types of systems, and that's a book in itself to kind of look at all the advantages of these systems. That is the new type of reactors employ. And I mean, look at the Navy. They always had smaller systems because on a submarine, let's say, you cannot put a massive reactor as what you use for power production on land, right? And those things are kind of been running forever, right? And because they are small, they're easy to handle. They're much easier to kind of operate. And so when we talk about small modular reactors, we kind of go in the direction of the sizes of systems that the Navy has, right? And even smaller, right? So there are different type of safety levels that you don't have for these super big power stations.
Mondo, let me give you an analogy. It's like a 1940s gasoline vehicle emissions versus the emissions of 2024.
Yeah, interesting.
Because I remember my first car, you open the hood and you could hide two of your buddies under the hood. It was just a small engine, a lot of emissions. I drive a Mercedes, and I opened the hood the other day, and Armando, there's not enough space to hide a sandwich under there. All this emission controls, everything else. Yeah, technology has changed quite a bit, and the same thing
That's
with refineries. Early refineries,
Yeah,
there was a lot of emissions.
risks are.
Yeah. So technology is bringing it under
But
control.
Ronald, in your case, you should buy an EV.
I think it's unethical and immoral to buy an EV because I know where the lithium and cobalt's coming from.
Ronald and Oliver, do you see that the U.S. Navy is happy with this solution? There is no other option. They will follow this direction of nuclear.
Oh, the Navy?
Yes.
It's been working for them for so long, and I think it's a mainstay. They're kind of now used to this type of reactor. They actually did play with a molten salt reactor, and it was running for 5 years way back. Molten salt technique is not new. It's just never been used on land for any application. But those reactors can take 30 times more energy out of nuclear material than the light water reactors. So effectively, you could extend those reactors for many more decades, even for the Navy, if you switch the systems, right? It's just that the Navy never adopted those, but who knows, right? Once we kind of deploy them on land and produce electricity. I give you one example. For example, in Texas, you have 2 nuclear power stations, and they take out the fuel when they call it spent because their power stations can no longer utilize it, and they put it on site of their power plants for storage, right? If you kind of now deploy these molten salt fast reactors, for example, and use that fuel that sits there on site on these power stations, you could power the entire state of Texas for 80 years just with a spent fuel.
Wow.
You wouldn't need anything else. You don't need any more windmills or solar panels or coal plants or gas plants or anything. You could effectively take what's there and run the entire state for 80 years. Now you can do the same thing for the US because there's a lot of nuclear power stations that have material sitting on site. And that would be enough to run the entire country 100% for over 200 years and produce electricity. just from what they call waste, which I call is actually fuel for the fast reactors. It's not really waste. It's only waste when you waste it, right? It's not.
Armando, let me make a comment because currently we're extracting a lot of resources from planet Earth, be it oil, lithium, cobalt, or whatever, and it's all being taken out of the Earth, but not being replaced. And it's going to run out eventually. How much oil is left? 100 years, 500 years, 1,000 years, who knows? And the same thing with lithium and cobalt. So we keep extracting this stuff, and Earth has been around 4 billion years, and it's going to be around without humans. And utilizing the nuclear technology, the fact that you use so little that lasts so long and serves so many people, is a way to conserve what we're extracting out of planet Earth.
That's right. And the other thing, what we haven't talked about is what is left over after the fast reactors are done extracting all that energy, right? People might ask, what's the waste of the waste?
You mean the destination of waste?
That's right. What's left over? Now, the story couldn't get any better because what's left over are elements of the platinum group in the periodic table, rare earths, and a bunch of other elements. So you would have in all the waste that exists, what the U.S. called nuclear waste right now, you would have about $1 trillion of metals as a waste product when you turn that waste into energy, and then what you have left over is still worth $1 trillion, right? One element that gets produced about 100 ounces per ton is rhodium, which is the most expensive precious metal. It's about $5,000 an ounce right now. You get about 100 ounces per ton, and they're 93,000 tons. So that's how much rhodium you get, right? That alone is worth $400 billion, right, at current market price. So it is even the leftover of the waste is not even waste, because you can actually use it for industry application, from rare earth platinum metals for contact plating and other things, right? So it's just tremendous value in there.
And do not forgetting, Ronald, that we use in food control, health systems and equipment, and so different applications. And this is okay. It's not okay when we talk about energy and talk about submarines. So the conclusion of our conversation could be that the problem is that the politicians don't understand the problem and the solution.
As Oliver mentioned, we have a system of reliable, emission-free electricity from nuclear that takes very little land and very little materials. And instead, the U.S., the wealthy countries, not only U.S., but Germany, the U.S., UK, instead, the wealthy countries are investing in wind and solar, which is unreliable electricity, non-dispatchable electricity, and it takes a lot of land and a lot of materials, and we're comparing apples and oranges.
Well, it's even worse, Ron, because when you look at the waste, the toxic metal waste that is in solar panels, that's actually more than you have in nuclear waste, right? So when you just say this is a toxic metal and this is a toxic metal, the toxicity of the metals and solar panels is even worse, right?
Cobalt, nickel, and different, and batteries, lithium, for instance.
And cadmium, right? They have cadmium in there. So it is, whatever is kind of from the propaganda machine is kind of made out as a clear solution. It's not clean. It's not reliable. It just has too many side effects, right?
That's right. Yeah, when we look at the end-to-end process from the mining to the rejections, of course. Yeah,
exactly.
That's right.
Exactly.
That's right. Excellent. Great conversation with Ronald Stein and Oliver Hemmers about the U.S. Navy using nuclear for more than 50, 70 years, something like that. Thank you so much, my friends. Thank
Okay,
you.
Armando.
It was a pleasure. Was a pleasure.
Appreciate it.
It's a pleasure for me too. Thank you so much. Bye bye.
Okay. Bye bye.